Hi everyone, we are from A4AS120527. Today we will present about experiment 6, which is high performance liquid chromatography, or known as HPLC. Before that, let's meet our team members. First, we have Nordiana binti Sumarno. Second, we have Amira Nafisa binti Azaman. Third, we have Nur Hafiza binti Kani. Fourth, we have Nur Shazwani binti Abdul Rahim. And lastly, we have Nur Anissa binti Elhemra. In this experiment, we will talk about introduction, objective, methodology, result and discussion, and lastly for conclusion. Firstly, I will explain about introduction. In introduction, I will explain about definition of HPLC, key features and advantages, and lastly, principle of operation. Definition of HPLC. HPLC is an advanced analytical technique that utilizes a liquid mobile phase to separate, identify, and quantify components in a mixture. It is highly versatile, capable of analyzing non-volatile and thermally unstable compounds such as organic and inorganic substances, biological samples, and synthetic polymers. Now I will explain about key features and advantages of high-performance liquid chromatography. Let's get started. Our first feature is greater sensitivity. HPLC is equipped with various detectors, allowing it to analyze even trace amount of substance. This makes it incredibly reliable for precise analysis. Next, we have reusable columns. This allows the multiple analysis, which significantly reduce operational costs. It's both efficient and cost-effective. Next, HPLC offers a wide application range. It's suitable for analyzing ionic species, large molecules, and compounds that are soluble in liquid. This versatility is one of its standout advantages. Finally, let's look at its practical application. HPLC is widely used in food safety, pharmaceutical, environmental analysis, and much more. It is a critical tool across multiple industries. Now is principle of operation. The sample dissolved in a solvent is injected to the system. Next, the liquid mobile phase under high pressure pushes a sample through a column with a stationary phase. Third, the mixture components separate based on their interaction with the mobile and stationary phase. Lastly, a detector identifies the separated components, creating a chromatogram where each peak represents a compound.
Next, the objective of this experiment is, first, to determine the retention time of a standard solution, caffeine. Second, to identify the caffeine peak in a soft drink sample. And lastly, to determine the amount of caffeine in a soft drink sample using the response factor method.
Next is methodology. Let me explain to you the functions and names of each component in HPLC instrument. The first one we have here is pump. The function is to force the mobile phase to flow through the backing and provides the mobile phase at a steady pressure and a flow rate. Secondly, injector, which is automatically adds samples to the streams of the mobile phase. Thirdly, column, the central element where separation takes place and function as analytical and guard column. Next is detectors, which tracks and measures the components that have been separated as they come out from the column, and bar property and solid property detectors. Not to forget data system, which is its function to gathers, handles, and evaluates the detector's data. And last but not least, we have mobile phase reservoir. The filtering, which contains the solvent or mobile phase that move the sample through the column.
First, we will start the HPLC instrument. Then all parameters will be entered by the help of available HPLC software. And these parameters are solvent ratio, flow rate, runtime, type of elution, etc. After creating the method, solvent of the mobile phase will be pumped by the HPLC pump from the solvent reservoir towards the degusser. Now these solvents will come to the degusser, and degusser is attached with a vacuum pump which will create high vacuum. Therefore, any gas or air dissolved in the solvent will be removed online, because this may create problem during elution. After degassing, solvents of the mobile phase will move towards the solvent mixing valve, and mixing of the solvents take place, which will help to produce uniform mobile phase. Now this mobile phase will run towards the pre-column or guard column. This guard column will remove any kind of impurity present in the mobile phase and protects analytical column from the impurities. In the next step, mobile phase will further move towards the analytical column then finally goes to detector. In this condition, blank mobile phase will run for 10 minutes at least, which gives proper conditioning of the HPLC instrument. Now we will inject the required amount of sample through sample injector by the help of a micro syringe. After injecting the sample, it will pass through the guard column, then it will enter into the analytical column, which contains stationary phase. Due to the difference in the affinity with stationary phase, compounds present in the sample will be separated inside the column and reaches to the detector and gives signals in the detector. Compounds having least affinity with stationary phase will reach to the detector first, which is indicated by blue color. Then moderate affinity compound will reach to the detector, which is indicated by red color.
I am going to explain about the HPLC procedure. There is two solutions that we need to prepare for caffeine standard solution, which is stock solution and working solution. For stock solution, 1.0 mg/ml, 10 mg of caffeine was accurately weighed into a 10 ml volumetric flask. Second, it was dissolved in distilled water. And third, the volume was made up to the mark with distilled water. For working solution, 0.1 mg/ml, which is 1 ml of solution A, was pipetted into a 10 ml volumetric flask. Then, the volume was made up to the mark with distilled water. Next, for sample preparation, about 10 ml of the soft drink sample, which is Coke, Pepsi or 100 plus, was poured into a small beaker. Second, a magnetic stir was used to remove any carbonation or sonification was performed if necessary. And third, a 2 until 5 ml aliquot was filtered through a 0.45 micrometer pore diameter membrane filter to remove particulate matter. After that, 10 microliter of solution B was injected to the HPLC to establish the retention time of caffeine. Fourth, the peak area of caffeine was measured. Fifth, a 10 microliter of the prepared soft drink sample was injected into the HPLC instrument. And last, the peak area was corresponding to caffeine was measured by referring to its retention time.
Next, we move on to result and discussion. From the first result, we can see that a single peak is observed at the retention time, which is 2.482 minutes. The area under the peak is 6249.48779 MAU with 100% relative area. This indicates a pure caffeine sample used as a reference standard for quantification. We move on to Levita sample. We can see that multiple peaks are observed with a significant peak at 2.479 minutes, likely corresponding to caffeine. The area for this peak is 1151.1124 MAU, which represents 17.6951% of the total area. Other peaks suggest the presence of additional compounds, possibly other ingredients, in the Levita drink. Next, Coke sample. We can see that a peak at 2.122 minutes corresponds to caffeine with an area of 2486.60387 MAU, contributing 28.3711% of the total area. Similar to Levita, other peaks indicate the presence of other compounds in the Coke sample. For discussion, the caffeine retention time in both Levita and Coke samples match closely with that of the standard caffeine RT 2.48 minutes, confirming of its presence in the samples. The areas under the caffeine peaks for Levita and Coke are smaller than that of the standard caffeine, indicating lower caffeine concentration in this product compared to the pure standard. Lastly, Levita has less caffeine relative to its total composition compared to Coke, as shown by the smaller relative area percentage for caffeine. Meanwhile, Coke has a higher caffeine peak area and relative percentage, indicating more caffeine in the sample.
Now let's move on for the last one, which is conclusion. In conclusion, the objective was achieved by determining the orientation time of standard caffeine 2.482 minutes and confirm its presence in Cook 2.481 minutes and Levita 2.479 minutes using HPLC. Employing the response factor method, we quantified caffeine in Cook 112.03 ppm and Levita 178.4 ppm, demonstrating the significantly higher caffeine content in the energy drink, which is Levita. This finding aligns with Levita's intent purpose of providing an energy boost compared to Coke, which is primarily a refreshing beverage. While HPLC was utilized in this study, alternative analytical technique exists. Gas chromatography could be suitable for volatile compound, albeit with necessary sample preparation. Mass spectrometry offers superior identification capabilities, providing detailed molecular information. For less stringent sensitivity requirement, UV-VIS spectrophotometry presents a simpler and more cost-efficient option for caffeine quantification. Fourier transform infrared spectroscopy also can be used to identify caffeine and related compounds. This alternative method offers flexibility depending on the specific analytical goals such as sensitivity, cost, or the needs for in-depth analysis.